MC cable is indeed a listed cable assembly. The National Electrical Code, specifically Section 330.2, defines metal-clad cable, or type MC, as a factory assembly of one or more insulated circuit conductors enclosed in a flexible or rigid metallic sheath or armor. This definition confirms its status as a pre-assembled cable system. Now let's delve into the specific exception you mentioned, 517.30 C3 exception number 5. This exception addresses the use of flexible wiring methods for luminaires, which include recessed lighting fixtures, incandescent and fluorescent fixtures, and other installed luminaires. The exception permits the use of several types of flexible cords, cables, or cable assemblies, but there are conditions. Firstly, the cords or cables must be listed for hard usage. Examples of these include hard usage cord designated HW, service entrance cables designated SE, service entrance oil resistant SEO, service entrance oil resistant water resistant U, service type SD, service type STO, service type S, service type SO, service junior type SJ, service junior oil resistant SDO, and service junior oil resistant water resistant SJ hard service cords. Secondly, and most importantly in context, MC cable is permitted but only under certain circumstances. The exception specifies that MC cable only shall be permitted. Thirdly, the wiring, whether exposed or concealed, is limited to individual luminaires. Fourthly, the luminaires must have a maximum load that doesn't exceed 600 volts, nominal, and 20 amps. Fifthly, the luminaires must be listed and installed according to their listing. Considering these requirements, you can use MC cable for wiring to your removable lay-in troughers in the operating rooms, assuming the luminaires meet the voltage and amperage limitations and are properly listed and installed. Now there are factors to consider given the location in an operating room, also known as an OR. Operating rooms have stringent requirements under the National Electrical Code, particularly concerning essential electrical systems, including emergency power. These requirements are designed to ensure patient safety and the continuous operation of critical equipment during power outages. Given these stringent requirements and the reliance on emergency power, particularly because the emergency lighting system is an EMT up to the point of transition to these lights, the situation warrants extra caution. It is advisable to consult with a qualified electrical engineer. An electrical engineer with expertise in healthcare facilities and the National Electrical Code would be able to thoroughly evaluate the specific installation, verify compliance with all applicable codes and standards, and ensure the safety and reliability of the electrical system. Such an evaluation would include confirming that the MC cable installation meets all the requirements of 517.30 C3 exception number 5, as well as any other relevant sections of the NEC. Furthermore, the electrical engineer can assess the adequacy of the emergency power system to handle the additional load imposed by the lighting fixtures and ensure that the system meets the requirements for healthcare facilities. In summary, while the NEC permits the use of MC cable for wiring to luminaires under certain conditions, the strict requirements for operating rooms and emergency power systems necessitate a careful evaluation by a qualified electrical engineer to ensure compliance and safety. The engineer can confirm the installation meets all applicable code requirements and that the emergency power system is adequate for the load. The purpose of electrical codes and standards is to ensure electrical safety and to protect people and property from hazards associated with electricity. This is achieved by establishing minimum requirements for electrical installations, including wiring methods, overcurrent protection, grounding, and equipment. These codes and standards are developed and updated regularly to reflect new technologies, safety concerns, and best practices. In the United States, the National Electrical Code, or NEC, is the most widely adopted electrical code. It is published by the National Fire Protection Association, or NFPA, and is updated every 3 years. The NEC provides comprehensive requirements for electrical installations in residential, commercial, and industrial buildings. It covers a wide range of topics, including wiring methods, overcurrent protection, grounding, equipment, and special occupancies. The electrical codes and standards are essential for ensuring electrical safety. By following these requirements, electrical contractors, engineers, and inspectors can help to prevent electrical fires, shocks, and other hazards. The NEC specifically is a comprehensive document. It is organized into chapters, articles, and sections, each addressing a specific aspect of electrical installations. The chapters cover general requirements, wiring and protection, wiring methods and materials, equipment for general use, special occupancies, special equipment, and communications systems. The articles delve into specific topics within each chapter, such as grounding and bonding, overcurrent protection, wiring methods for specific locations, and requirements for different types of equipment. The sections provide detailed requirements for specific aspects of an electrical installation. They may cover topics such as conductor sizing, overcurrent protection device ratings, grounding electrode systems, and installation methods. Understanding the structure of the NEC is crucial for navigating the code and finding the requirements that apply to a specific situation. It is not enough to simply read the code, it is also important to understand the intent behind the requirements. The NEC is written to provide a minimum level of safety, and it is up to the electrical contractor, engineer, or inspector to ensure that the installation meets or exceeds these requirements. One way to understand the intent behind the NEC requirements is to consult the NEC Handbook. The NEC Handbook provides explanations and interpretations of the code requirements. It also includes examples and illustrations to help clarify the meaning of the code. Another way to understand the intent behind the NEC requirements is to attend training courses or seminars on the NEC. These courses can provide valuable insights into the code and help to clarify any ambiguities. It's not a static document, it evolves with technology and experience. The code is updated every 3 years to reflect new technologies, safety concerns, and best practices. This means that electrical contractors, engineers, and inspectors must stay up to date with the latest edition of the NEC. There are several ways to stay up to date with the NEC. One way is to subscribe to the NFPA's online newsletter. The newsletter provides updates on changes to the NEC as well as other news and information related to electrical safety. Another way to stay up to date with the NEC is to attend training courses or seminars on the latest edition of the code. These courses can provide valuable information on the changes to the code and how they will affect electrical installations. Compliance with the NEC is essential for ensuring electrical safety. Failure to comply with the NEC can result in electrical fires, shocks, and other hazards. In addition, failure to comply with the NEC can result in fines, penalties, and even criminal charges. To ensure compliance with the NEC, it is important to hire a qualified electrical contractor who is familiar with the code. The electrical contractor should be licensed and insured and should have a proven track record of complying with the NEC. It is also important to have the electrical installation inspected by a qualified electrical inspector. The electrical inspector will verify that the installation complies with the NEC and that it is safe to operate. In addition to the NEC, there are other electrical codes and standards that may apply to a specific installation. These codes and standards may be developed by state or local governments or by industry organizations. It is important to be aware of all applicable electrical codes and standards and to ensure that the electrical installation complies with these requirements. The NEC is a comprehensive document that covers a wide range of topics. It is important to understand the structure of the NEC and the intent behind the requirements in order to properly apply the code. Staying up to date with the latest edition of the NEC is essential for ensuring electrical safety. Compliance with the NEC is essential for preventing electrical fires, shocks, and other hazards. A qualified electrical engineer is also important. The role of an electrical engineer is to design, develop, test, and supervise the manufacturing of electrical equipment. They work on a wide range of projects, from power generation and distribution to electronics and communications systems. The electrical engineers must have a strong understanding of electrical theory, mathematics, and physics. They must also be able to use computer-aided design or CAD software to create electrical schematics and layouts. Electrical engineers typically work in offices or laboratories. They may also travel to job sites to oversee the installation and testing of electrical equipment. The job outlook for electrical engineers is expected to grow in the coming years. This growth will be driven by the increasing demand for electricity, as well as the need for new and improved electrical systems. The specific tasks and duties of an electrical engineer can vary depending on the industry and the specific job. However, some common tasks and duties include designing electrical systems, developing electrical equipment, testing electrical equipment, supervising the manufacturing of electrical equipment, writing technical reports, and providing technical support. To become an electrical engineer, one must typically earn a bachelor's degree in electrical engineering from an accredited university. The curriculum for an electrical engineering degree typically includes courses in electrical theory, mathematics, physics, computer programming, and engineering design. Many electrical engineers also pursue a master's degree in electrical engineering to further their knowledge and skills. A master's degree can also help electrical engineers to advance their careers. Electrical engineers work in a wide range of industries, including the power industry, the electronics industry, the communications industry, and the aerospace industry. They may also work for government agencies or consulting firms. The specific skills and knowledge required for a job as an electrical engineer can vary depending on the industry and the specific job. However, some common skills and knowledge include a strong understanding of electrical theory, mathematics, and physics, the ability to use computer-aided design software, the ability to write technical reports, the ability to provide technical support, and problem-solving skills. The field of electrical engineering is constantly evolving, so it is important for electrical engineers to stay up to date on the latest technologies and trends. This can be done by attending conferences, reading technical journals, and taking continuing education courses. Electrical engineers play a vital role in our society. They design and develop the electrical systems that power our homes, businesses, and industries. They also develop the electronic devices that we use every day, such as computers, smartphones, and televisions. Electrical engineers are essential for ensuring that our society has access to reliable and affordable electricity. An electrical engineer, particularly one with experience in healthcare facilities, possesses a deep understanding of the unique electrical requirements and safety considerations within such environments. This specialized knowledge extends beyond the general electrical codes and standards, encompassing the specific regulations and guidelines that govern electrical systems in hospitals, clinics, and other healthcare settings. Firstly, they are well versed in the requirements for essential electrical systems, which are critical for maintaining patient care during power outages. These systems include emergency power supplies, such as generators and uninterruptible power supplies, or UPS, and the distribution networks that deliver power to essential equipment and areas. The engineer ensures that these systems are designed, installed, and maintained in accordance with the applicable codes and standards, such as NFPA 99, which covers healthcare facilities. Secondly, they have a thorough understanding of the grounding and bonding requirements for healthcare facilities. Proper grounding and bonding are essential for minimizing electrical noise and preventing electrical shocks to patients and staff. The engineer designs the grounding and bonding systems to meet the specific needs of the facility, taking into account the types of equipment used and the potential for electrical hazards. Thirdly, the electrical engineer is familiar with the requirements for isolated power systems, which are used in critical care areas, such as operating rooms and intensive care units, or ICU. Isolated power systems reduce the risk of electrical shock by isolating the patient from ground. The engineer designs and installs these systems in accordance with the applicable codes and standards. Fourthly, they are knowledgeable about the requirements for electrical equipment in hazardous locations. Hazardous locations are areas where flammable gases, vapors, or dust may be present. The engineer ensures that electrical equipment used in these areas is designed and installed to prevent ignition of the hazardous materials. Fifthly, the electrical engineer is able to conduct electrical safety inspections and audits of healthcare facilities. These inspections and audits help to identify potential electrical hazards and ensure compliance with the applicable codes and standards. The engineer also provides recommendations for corrective actions to address any identified deficiencies. Sixthly, in addition to technical expertise, the electrical engineer possesses strong communication and interpersonal skills. They are able to effectively communicate with healthcare professionals, administrators, and other stakeholders to explain complex electrical concepts and to address their concerns. They also work collaboratively with other members of the design and construction team to ensure that the electrical systems meet the needs of the facility and its patients. Furthermore, an experienced electrical engineer understands the importance of patient safety and works diligently to ensure that the electrical systems in healthcare facilities are designed, installed, and maintained to the highest standards. They are committed to providing a safe and reliable electrical environment for patients, staff, and visitors. Consulting with a qualified electrical engineer is crucial for ensuring the safety and reliability of electrical systems in healthcare facilities. Their specialized knowledge and experience can help to prevent electrical hazards and to ensure that the facility meets all applicable codes and standards. The NEC, specifically Article 517, addresses healthcare facilities. This article provides additional requirements for electrical installations in healthcare facilities to ensure the safety of patients and staff. Article 517 covers a wide range of topics, including essential electrical systems, grounding and bonding, isolated power systems, and electrical equipment in hazardous locations. One of the key requirements of Article 517 is the need for an essential electrical system, or EES. The ES is designed to provide backup power to critical areas of the healthcare facility during a power outage. The EES must be capable of providing power to life safety systems such as emergency lighting and fire alarm systems, as well as critical equipment such as operating room equipment and life support systems. Article 517 also includes specific requirements for grounding and bonding in healthcare facilities. Proper grounding and bonding are essential for minimizing electrical noise and preventing electrical shocks to patients and staff. The grounding and bonding systems must be designed and installed to meet the specific needs of the facility, taking into account the types of equipment used and the potential for electrical hazards. Isolated power systems are another important requirement of Article 517. Isolated power systems are used in critical care areas to reduce the risk of electrical shock by isolating the patient from ground. The isolated power systems must be designed and installed in accordance with the applicable codes and standards. Article 517 also includes requirements for electrical equipment in hazardous locations. Hazardous locations are areas where flammable gases, vapors, or dusts may be present. The electrical equipment used in these areas must be designed and installed to prevent ignition of the hazardous materials. Article 517 is a complex and comprehensive article that provides specific requirements for electrical installations in healthcare facilities. Compliance with Article 517 is essential for ensuring the safety of patients and staff. A qualified electrical engineer with experience in healthcare facilities is essential for designing and installing electrical systems that meet the requirements of Article 517. The electrical engineer must be familiar with the latest edition of the NEC and must have a thorough understanding of the specific requirements for healthcare facilities. In addition to the NEC, there may be other codes and standards that apply to electrical installations in healthcare facilities. These codes and standards may be developed by state or local governments or by industry organizations. It is important to be aware of all applicable codes and standards and to ensure that the electrical installation complies with these requirements. The goal is to provide a safe and reliable electrical environment for patients, staff, and visitors.